Similar solids. Our objectives today are to be able to use similar geometric objects in 2 or 3 dimensions to compare ratios between side lengths, perimeters, areas, and volumes. Also to determine how changes in 1 or more dimensions of an object affect area and/or volume of the object, and determine how changes in area and/or volume of an object affect 1 or more dimensions of the object, and solve real-world problems about similar geometric objects. If you remember last time, we changed just part of the solid. Now we're going to change all the measurements, making the objects similar. So we'll start by finding ratios, making the chart EEAV. We'll talk about what that means momentarily. First, let's highlight some terms that we maybe haven't seen in a while. Similar polygons. These similar polygons have the same shape but different size. The angles are congruent and the sides are proportional. A scale factor. We've seen that word before when we've talked about a dilation. Remember the word dilation? A dilation stretches or shrinks the object, making the objects similar. The scale factor is the ratio of the 2 corresponding lengths. Recall that a ratio is an expression relating to quantities. Sometimes it may look like a fraction, like A over B. Sometimes it's written as A colon B. A proportion is an equation relating to ratios. Let's talk about computing and using ratios for similar figures, making the chart EEAV. So we start with the ratio of corresponding lengths, any corresponding lengths. This is generally where we put the scale factor, because we get the scale factor from the ratio of corresponding lengths. Recall that area is 2 dimensions. So when we think of going from the scale factor, or the ratio of corresponding lengths, to a ratio of areas, we want to remember that we always square to get areas, like centimeters squared, right? Lengths we would measure in centimeters, areas we would measure in centimeters squared, and volumes, because it's 3 dimensions, we would measure in centimeters cubed. So when we go from scale factor, or lengths, to areas, we want to think of taking the scale factor and squaring it. So 2 squared and 5 squared makes 4 over 25, and this is the ratio of areas. If we're going backwards from the ratio of areas to the corresponding lengths, going this way, then we want to do the opposite of squaring, taking the square root of 9 and the square root of 4. The square root of 9 is 3, the square root of 4 is 2. So the scale factor, or the ratio of lengths, is 3 over 2. So we know going from the lengths to the areas, we square it. Going backwards from the areas, we take the square root. Remember, because volume is 3 dimensions and we have cubic units, to go from scale factor to volumes, what do you think we'll do with those numbers? That's right, we'll cube them instead of square them. So 2 cubed and 5 cubed. 2 cubed, 2 times 2 times 2 makes 8, and 5 times 5 times 5 makes 125. If we're going backwards from volumes to scale factor, what's the opposite of cubing? Taking the cubed root. The cubed root of 2 over, oops, my mistake. That should say the cubed root of 5. I mean the cubed root of 8. Cubed root of 8 over the cubed root, notice the 3 goes in that little corner of the root symbol, over the cubed root of 125. The cubed root of 8 is 2 because 2 cubed makes 8, and the cubed root of 125 makes 5. So that's going backwards from volumes to scale factors. To fill in the rest of this chart, we always start from the scale factors. Let's make a note about that, how we always come to this column first. Now, to make things a little bit easier, we're going to call this the everything else column. So we'll always come to EE first. Why everything else? Because the only thing that can go in the area column is areas. We're going to write A and put a little 2 here to remind us this is the A area column and it always gets squared. This will be our V column and we'll put a 3 here to remind us that volume always gets cubed. Everything else, if it doesn't have the word area or volume, goes in this first column. So we always come to this column first. Then we can go fill in the other columns. So from 2/5 to get over here, we do 2 squared over 5 squared, and that makes 4/25. From 3/2, we do 3 cubed over 2 cubed, and that makes 27/8. And that fills in the columns. So think about, where would these go? If they said the ratio of perimeters, well, does that say area or volume? It does not, so that's everything else. Scale factor, everything else. Lateral area, I see the word area, so that goes in the A column. Surface area, I see the word area, so that goes in the A column. Height does not have the word area or volume, so that goes in the everything else column. Ratio of sides does not have the word area or volume, everything else. Circumference, everything else. Diameter, everything else, and radius, everything else. Remember, EE stands for everything else because it's not area or volume. Next, we'll talk about how we can apply this.